A permanent magnet is a room temperature superconductor of the zero-point energy field. It is very difficult to use the power flowing through permanent magnets to make a motor powered by them alone. But in spite of that, many people are drawn to making a permanent magnet only motor and using it to generate useful power. The Dietmar Hohl design is one of the very few which can readily be made and tested at home. It's a circular design which is made from quite a number of different magnets. They're arranged in a V shape, and the position of the magnets and the direction of their poles is shown in this accurate drawing here. It's a clever design, and it has the magnets angled relative to the surface of the drum that they're inserted into. Even if it's only built roughly, it still operates as Jes Askenius of Denmark has demonstrated. This is his build here, which he put together in about half an hour. The magnets he put in, he didn't angle, but it still ran perfectly well. The problem is that almost all magnets have a symmetrical magnetic field, while what is needed for a magnet-powered motor is an asymmetrical magnetic field. Consequently, magnets have to be combined in ways which distort their normal field shape. You will notice that in a Hohl motor the drive magnets are angled, and that is an important feature of using magnets in motors. Schools currently teach that the magnetic field surrounding a bar magnet is like this, with the field lines of force going out of one end of the magnet and entering the other end of the magnet. This is deduced by scattering iron filings on a sheet of paper held near the magnet. Unfortunately, that's not a correct deduction, as the iron filings distort the magnetic field by their presence, each becoming a miniature magnet in its own right, and that alters the magnetic properties of the space around the magnet in the plane of the iron filings. More careful measurements show that the field actually produced by a bar magnet is like this. You have many lines of force, but they concentrate around the corners of the rectangular bar magnet. They actually fan out in three directions, so while it's shown as a couple of circles here, the reality is that it's fanning out in something like a golf ball shape at each corner. This is a three-dimensional field, and it's very difficult to assess because you can't see the field. The lines of force are like a golf ball or a soccer ball with the corner of the magnet in the center of the ball. Actually, there are many layers of lines of magnetic force, so it's like having a whole series of gradually bigger and bigger spheres, all centered on the corner of the magnet. It's extremely difficult to draw those lines and show them clearly on a two-dimensional surface. Howard Johnson's book, The Secret World of Magnets, gives you a good idea of the actual lines of force around a bar magnet. The arrangement of these lines of magnetic force is not generally known, and if you Google magnetic lines of force images, you'll only find the fiction taught in schools. However, the important fact is that there is a rotating magnetic field at each corner of a typical bar magnet. It follows then that if a row of magnets is placed at an angle, then there will be a resulting net force in a single direction. For example, if the magnets are rotated 45 degrees clockwise, then the result will be like this. The magnets are coming up at an angle, and the uppermost corner of those magnets has its own rotating set of lines of force around the corner of the magnet itself, and that gives you a net magnetic force from left to right in this particular diagram. With this arrangement, the opposing corners of the magnets are lower down, and so there should be a net magnetic force pushing to the right just above the set of magnets. However, the situation is not as simple and straightforward as you might imagine. The additional lines of magnetic force, which have not been shown in the diagram above, act further out from the magnets, and they interact, creating a complex composite magnetic field. It's frequently found that after 4 or 5 magnets aligned at those angles, that you need to have a short gap between the 4th or 5th magnet and the next one in the row. Joseph Newman has pointed this out and has determined what we call a magnetic flow is actually the zero-point energy field flowing through a permanent magnet along the path of a cylindrical helix. So the flow of the zero-point energy field goes round and round and round, and then spirals round in a tight circular repeating sequence. The attraction and repulsion of magnetic fields is caused by the direction of the flow along those curved helixes. If the direction of flow is clockwise in this one and anti-clockwise in this one, or rather clockwise in both of those, they don't mesh up properly where they meet. So there is a repulsion between the fields that are both going in the same direction there. The same applies if you're looking at electricity in the negative charge components, or if you're looking at magnetics in the north and south orientation magnetic poles. But as they're going in the same direction, if they are pushed close together, then they clash where they nearly touch, and that tends to push them apart. And the opposite effect is if you have a north and a south pole, when the fields move together, they're going in the same direction, and you get an attraction of the magnetic fields where they meet like that. Is slightly inaccurate to describe it exactly like that, because you will find with experimentation that the repulsion north pole to north pole is actually greater than the repulsion of south pole to south pole. But that's something that is not something you need to concern yourself with to any great degree. If you have opposing fields north to north repulsing each other, then it is liable to detract from the power of the magnet eventually. Some people have produced motors and discovered that after 3 months of running that they stopped operating altogether. It's not a major problem, because you can reinstate a magnet in a split second by putting it inside a coil of wire and pulsing that coil of wire with a high current. It only takes one pulse to actually regenerate the magnet. And you can use fancy things like neodymium magnet material to get a powerful magnet, or you can use ordinary mild steel, and that will certainly give you quite a good permanent magnet. There are 2 boys, one is called Anthony and one is called Andreas, and they've used this magnet arrangement of angled magnets to create a magnetic track. They've had a lot of fun sending a magnet sliding between 2 of these rows of angled magnets. Initially they used the cheaper ceramic magnets and got a very satisfactory movement when using a neodymium magnet as the moving component. You will notice that they have managed a row of 18 ceramic magnets on each side of the track, and the results which they are getting are very good. They've got 3 videos on the web at the present time. The links are shown here, and as of the 22nd of May 2020, those videos were still in place on YouTube. The moving magnet is made up of four 12mm by 12mm by 12mm, or if you prefer half inch by half inch by half inch, neodymium magnets attached together under their own power, north-south, 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 to form a single magnet which is 48mm long, 12mm wide, and 12mm deep in size. That's the way that the magnet looks, and remember, it's only about 2 inches long. They have not disclosed all of the details of what they're doing, accidentally rather than by intention. The ceramic stator magnets are 48mm by 20mm by 10mm, with the poles on each of the main faces. They position each magnet with its north pole facing towards the track, and they angle the magnets at 45 degrees. There's a 15mm gap between the stator magnets and the moving magnets on both sides of the track. Wooden strips direct the moving magnets and keep them in a straight line. Neodymium magnets have very different characteristics to those of ceramic magnets, and that's not just the strength of the magnetic field either. It's not unusual for experimenters to find that devices will work well with one type of magnet but not with the other type. Here the developers have tried using 2 sets of 5 angled neodymium magnets on each side of their track, and the result was a more powerful thrust on the moving magnets. The magnets that they used are held in place in this photograph, as you can see, by wooden dowels driven into their wooden base plank. They used those in order to avoid any magnetic fastening material which could alter the magnetic field. The next step would be for them to power a motor using their magnetic track technique. However, this has been tried many times, and the conclusion is that it is very hard indeed to change a straight magnetic track into one which forms a complete circle. Therefore I would suggest the following arrangement, which uses only the straight line push demonstrated by the boys. For that, you have a simple disc rotor which has got 4 magnets on of the type used to move down the magnetic track attached to the underside of the disc. You have then positioned just outside them, with the same dimensions that the boys used, of 2 sets of 5 angled magnets for each of the magnets attached to the rotor disc. The rotor disc is obviously on an axle shaft which is in a bearing to allow it to spin freely. This is a top view of the arrangement. On the underside of the disc you see there are 4 separate rotor magnets, and then attached to the immovable stator locations you have got 4 sets of pairs of 5 angled magnets. So there are 10 magnets on the stator at each of 4 locations, which is 40 magnets, and then you've got the 4 composite magnets on the underside of the rotor disc. This arrangement avoids trying to turn the magnetic field around to match its start. It uses 4 separate straight magnetic field strips. Doesn't matter if the rotor axle is horizontal or vertical. If the disc spins well, then sets of 2 air core pickup coils can be positioned beneath the rotor and between the stator magnet arrays, so that electricity is generated as the rotor magnets pass by overhead. If a constructor decides to attach 2 rotor discs to the one rotor shaft, Then the two rotors should be positioned so that the rotor shaft gets pushed every 45 degrees of rotation rather than every 90 degrees as shown here. This style of motor is definitely within the scope of the average person to build, should they be inclined to do so. I've been asked to say how I personally go about constructing a prototype of this nature. As I have very limited constructional skills, I would do it like this. I start by constructing a support base with a high quality bearing mounted on it. A square of wood or fiberboard, which is MDF, can then be attached to the bearing and centered on it. Then, after clamping the base to a fixed surface and finding a secure support for a pencil, you can spin the board so as to mark a perfect circle positioned exactly on the center of the bearing. Then I would disconnect the wood again and cut around the pencil line very carefully, smoothing the edges of the disc gently with fine sandpaper. Screwing the disc back in place, a spin should confirm that the edge of the disc appears to stay steadily in place, with no wavering of the edge inwards and outwards. Actually, if the disc is not perfect, that's not really a major problem, as it is the rotor magnets which need to be positioned accurately. And for that, another pencil line can be produced by spinning the disc when the desired position for the rotor magnets has been located. Permanent magnets vary enormously in size and strength, so when magnets are purchased, it's a matter of testing them using a track of the type used by Anthony and Andreas. The stator magnets are angled at about 45 degrees to the track, and with just 4 on each side, it is a case of finding the spacing between the two sets of angled magnets which pushes the stator magnets furthest along the track. While it's interesting to see a permanent magnet motor rotate entirely on its own, we really wanted to do useful work, and so we mount output coils marked in red here on this diagram to allow the rotor magnets to pass over them, exactly over them. That's over the core of them, each electromagnet coil. An effective method of connecting the output coils together comes from Denis Sabarin of France. The coils are wound as bifilar coils, that is, wound with 2 identical lengths of wire side by side for every turn, using 50 grams of 0.19 mm diameter wire in each coil. That produces coils which weigh about 100 grams plus the spool weight. Then the coils are connected like this. The first winding of the first coil goes to the first winding of the second coil, which goes to the second winding of the first coil, then on to the second winding of the second coil. They're arranged in 4 pairs of coils together, irrespective of their location on the board. This method of connection has been found to be very effective for coils which have magnets moving past them, and the output might be used to power a joule thief to charge batteries of 12 volts or higher voltage. The arrangement like that is the coils produce a voltage, probably best with a capacitor across it, but not essential, and that then is used to power standard joule thief with its own bifilar coil, one winding feeding a 1K resistor through to the base of a transistor. In this case, a 2N2222 is likely to be very satisfactory. You have got diodes, I would suggest 1N4148 type there. You put several of them across each other to increase the ease of flow through the diodes, and that then feeds the battery which is being charged, and that can be a much higher voltage than just 1.5 volt battery, which is normally used to power a dual teeth arrangement. An alternative to arranging magnets in such a way as to distort them symmetrical fields is to make a magnet motor by moving a permanent magnet in such a way as to give a continuous drive to rotor magnets. There are many motors of that type. For example, Donald Kelly's design, where a motor is used to move the stator magnets, which are all linked together. It makes the pivot arm here rock backwards and forwards, and it's arranged so that it clears the passing rotor magnets, which are projecting out of the board, typically out of the rotor board. And that works very effectively, though it does make some noise, obviously, with the mechanical movement. Alternatively, you can use electrical shielding, like in the very successful Flynn magnet motor. There, the coils marked in green are powered up by a circuit in the correct sequence, and that drives each of the magnets on the output power shaft around very strongly. The magnets shown here in grey are circular disc magnets with the north face on the upper side, the south face on the lower side, and the more you put on the shaft, the more powerful the motor is. And with only a dry battery of 9 volts, that motor can reach 20,000 revs per minute. Making a magnet motor is not the easiest thing to do, as you can't see a magnetic field, but it is perfectly possible to make an effective magnet motor if you set your mind to it, and the methods shown in this particular document would be sufficient for you to have a very successful outcome to your project, and I wish you every luck in it.